This video is about implicit versus explicit solutions of differential equations. We're also going to verify that a given relation is an implicit solution to a differential equation. So let's start with an example. If I have x squared plus y squared equals 4, that represents this relation. If I graph it in the xy plane, we have a circle centered at the origin with radius 2. Now if I take this relation and I differentiate implicitly with respect to x, so I'm differentiating this side with respect to x and differentiating this side with respect to x, and I'm treating y as a function of x the whole time. That WRT there just means with respect to, and we're treating y as a function of x. If I do that, the derivative of x squared with respect to x is just 2x because of the power rule. The derivative of y squared with respect to x is the derivative of y squared with respect to y, which is 2y by the power rule, times the derivative of the inside by the chain rule. Since y depends on x, the derivative of y with respect to x is the derivative of the inside. And of course, the derivative of 4 is 0. So then if I take this equation and I solve for dy dx, I get this. So we have a differential equation. Now in this class, most of the time, we don't start here and end up here. We start here, and the question is, what function satisfies this equation? What function y can I take the derivative of? Or when you take its derivative, you're going to get negative x divided by the original function back. So this is the differential equation, and this is the relation that we started with. Sometimes we want to go backwards. Instead of going from here to here by differentiating implicitly, we're going to want to go from here back to here. This is a relation that satisfies this differential equation. This relation is called an implicit solution. I think the easiest way to think about implicit solutions is to think of them as a relation where y, or the dependent variable, is not isolated. You've got some function of x and y over here and potentially some function of x and y over here. But your dependent variable is not by itself. It's related to the other variables in the equation, well, by the equation. The equation tells you how those variables are related to each other. Now, this implicit solution corresponds to actually two explicit solutions. If I wanted to, I could take this equation and solve for y by subtracting x squared from both sides and taking the square root of both sides. Don't forget your plus or minus. There are actually two functions there. That's y equals the positive square root of 4 minus x squared, and y equals the negative square root of 4 minus x squared. So the positive square root, that's the top half of our circle. That's that function. And the negative square root, that's where y is negative or possibly 0. That's the bottom half of our function, or our relation up here, the graph of our relation. And so you see this relation actually corresponds to two solutions. These are called explicit solutions of that differential equation. If you take the derivative of this and you substitute it in over here, and you take the function itself and you substitute it in over there, you're going to get the same thing on both sides. This function satisfies that equation, and this function satisfies this equation. Now, this relation also satisfies this equation in that there is a function y out there that satisfies this differential equation and satisfies this relationship. And I actually found two of them right here. There are two functions y that satisfy this relationship and satisfy that differential equation. Now you could also, think of this differently. If I wanted, I could take the reciprocals of both sides. And I know you really shouldn't treat this like a fraction, it's not a differential of y over a differential of x, but it does turn out that if you flip that, you get the derivative of x with respect to y. That's actually legal. We studied that a little bit in Calculus 1. That 1 over this function is actually this function. And you flip both sides and you get an equivalent relationship. So this is implying, just from context, that y depends on x, and the derivative of y with respect to x is negative x divided by y. We could have just as easily thought of x as the dependent variable. I could say, instead of y depending on x, what if x depends on y? Well, then the derivative of x with respect to y would be negative y over x. So we have two explicit solutions to this differential equation right here, where y is by itself and you've got a function of x over here. These are functions that satisfy this equation and satisfy this differential equation. There are actually two more explicit solutions that correspond to this relationship, and they just come from taking this equation and solving for x instead of solving for y. So let's draw our circle again. And it doesn't have to be perfect. Oops, there we go. So we've got our circle, radius 2 centered at the origin. If I take this and solve for x by first subtracting y squared from both sides and then taking the square root, don't forget your plus or minus, I get two functions. So I've got x equals the positive square root of 4 minus y squared and x equals the negative square root of 4 minus y squared. Positive square root, that's where x is positive or possibly 0. That's over here. The negative square root, that's where x is negative or possibly 0. That's on the other side. This is a function, or these are two functions that satisfy this differential equation and they satisfy this relationship. So these are explicit solutions of the differential equation as well. So we actually have 4 explicit solutions, and I guess you could say we have infinitely many of them because we could restrict the domain to be smaller. I could take any little subset of that piece and it would be an explicit solution to this differential equation. Or I could take any little subset of this here or that there, and that would be an explicit solution to the differential equation. But if we're taking the largest intervals possible, these are our explicit solutions. I've got these two guys, those two functions, top half and bottom half. And I've got these two functions, the left half and the right half. All of those satisfy these two differential equations. So all of that was to say, it's leading up to this idea, what is an implicit solution of a differential equation? And this is what I'm calling an implicit solution. The easiest way to think about it is a solution where your dependent variable y is not by itself. Like that's an implicit solution. That's an explicit solution. But more formally, like how would I be able to tell if this is a solution of this equation, or if to say that this is a solution of that differential equation? Well, we need a better definition than that. So let me give you a definition now. An implicit solution is just a relation. And I'm going to write f of x, y equals k. It's just some function of x and y equals a constant. And you could have a function of x and y over here and a function of x and y over here, and you can move them over. It doesn't matter. This is just a relationship between x and y. This relation is called an implicit solution. of an ordinary differential equation, or of a differential equation in general, on an interval, which I'll label I, provided that there's some function. So I'll say provided there is at least one function that satisfies both the differential equation and the relation. So we're saying there's at least one function, and that function can be y as a function of x, or it can be x as a function of y, that satisfies this relationship. Like in this concrete example, we had x squared plus y squared equals 4, and the differential equation, which could be this one or it could be this one. So that's what an implicit solution is. Now, in order to come up with this differential equation, I differentiated implicitly. So if somebody says that here's an implicit solution of this differential equation, prove it or verify that this relation is an implicit solution of this differential equation, all you do is exactly what I did at the very beginning. You start with that relation and you start differentiating. You differentiate both sides with whatever variable you think of as the independent variable, and you try to make it look like the differential equation. If you're able to do that, then pretty much, or almost all of the time, that's going to be a solution of the differential equation. Now, technically, we should also check that there's actually a function out there that satisfies the differential equation and the relation, and the functions might look like this. But most of the time, the algebra is such that we can't get y by itself, or we can't get x by itself, because if we could, we would, and we wouldn't be relying on an implicit solution to begin with. So for our purposes, if I want to verify that a relation is an implicit solution of a differential equation, all I do is differentiate implicitly and try to make what I started with through differentiation look like the differential equation that they gave me. So here is an example. They were asked to verify that natural log of 2x minus 1 over x minus 1 equals t is a solution of the differential equation dx dt equals 1 minus x times 1 minus 2x. And I'm just trying to verify that this relation satisfies this. Now I could just start differentiating both sides. Notice that x is being treated as the dependent variable and t is being treated as the independent variable. So I would probably differentiate both sides with respect to t. But I know I can do a little bit of algebra first to simplify this, to simplify my calculations. I'd rather not have to take the derivative with respect to t of natural log of this quotient when I've got log rules that would allow me to simplify this, and also exponential rules that would allow me to get rid of that log. So I think what I'm going to do, rather than starting with implicit differentiation with respect to t, is I'm going to manipulate that equation a little bit first. Why? Just because I want to make the differentiation easy. As long as I follow the rules of algebra, excuse me, this is legal. So let's exponentiate both sides to get rid of that log. And now you've got 2x minus 1 over x minus 1 equals e to the t. And I like this better. When I differentiate both sides with respect to t now, I have to use a quotient rule over here, and the derivative of e to the t with respect to t is just e to the t. So it's going to make it nice and simple. So let's see, what did I start by doing? We start with the relation that we're given. And then I simplified it Again, that's just for the purpose of making it easier to differentiate with respect to t. Now we're going to differentiate implicitly with respect to t. And now remember, whenever you do that implicit differentiation, you want to remember that x is not constant. This is not a partial derivative. You want to remember that x depends on t. We're assuming that x can be written as a function of t. And now we're taking the derivative of this guy with respect to t. So I've got a quotient over here. So I'm going to use the quotient rule. Just in case you don't remember, let's put that quotient rule out there. If you have the derivative of f over g, you may have heard this mnemonic, It's low d high minus high d low over low low. And the d is an operator. It applies to whatever's in front of it. So it's the bottom function times the derivative of the top function. If this is the high function and that's the low function, low d high is g f prime. Then we're saying minus high d low, so it's f g prime over low low. Okay, so that's what we're going to apply right here to this guy. So it's low, bottom function, d high, with respect to t, remembering that x is a function of t, minus high, d low, all over low low, bottom function squared. We've got all these little sing-songy mnemonics. They help, they really do. I learned that in high school. I will be forever grateful to Mr. Pink, who taught me AP Calculus. And I will never forget it. Every time I do a quotient rule, I say to myself, low d high minus high d low over low low. Okay, so now we're here. And of course, the derivative of e to the t is e to the t. Now, whenever you're taking the derivative of something like this and the variables don't match, you take the derivative with respect to whatever variable's there. So we take the derivative of 2x with respect to x, that gives me a 2. And then we multiply by the derivative of this variable with respect to this variable. Now again, the reason for that is that we're using the chain rule. That's where those guidelines for implicit differentiation come from. The derivative of 2x minus 1 with respect to t is 2 times derivative of x with respect to t. So we take the derivative with respect to x first, we get the 2. Then we multiply by the derivative of x with respect to t. Or alternatively, you can think of this as x of t. What's the derivative of 2 times x of t? It's 2 times x prime, or 2 times dx dt, which is the same thing. And of course, the derivative of -1 is 0. So we lose that guy, bring that guy down, and the derivative of x minus 1 with respect to t is the derivative of x minus 1 with respect to x, which is just 1, times dx dt, all divided by x minus 1 squared, and that equals e to the t. Okay, now we're trying to make this equation that we started with, that was our implicit solution. We're trying to make this look like this. So we need to get dx dt by itself. And our hope is that if we get dx dt by itself, the expression on the right-hand side is going to look like this. That's our hope. Cross your fingers. We're just really hoping that that actually works out. So in order to do that, let's factor out the dx dt from that numerator. We can actually bring it off out of the fraction entirely. So I've got dx dt here times, and then I've got 2 times the quantity x minus 1. I think I'll distribute there right now. That's 2x minus 2. Minus this quantity. Don't forget to distribute your negative. If you forget to distribute your negative, that guy will have the wrong sign. So I'll have negative 2x minus a negative 1 is plus 1, all over x minus 1 squared. And that's nice, the 2x's reduce. And I've got a negative 2 plus 1, which is just a negative 1. And that's multiplied by dx dt. And that equals e to the t. Now I'm trying to get this guy by itself, so I'll just multiply by the reciprocal of this guy. I don't know where, well, actually I do know exactly where I started personifying functions. There was a tutor in the math lab where I worked for years who had a habit of personifying functions. He'd talk about this guy and that guy, and I picked it up from him. Okay, so we multiply by the reciprocal of that, and we get dx dt equals negative 1 times e to the t times x minus 1 squared. Because dividing by negative 1 is the same as multiplying by negative 1. Now, if you're saying to yourself, wait a minute, that is not what we started with, you're absolutely right. It isn't what we started with. The claim is that this is an implicit solution of this. They said to verify it. They didn't say determine if it's a solution. They said to verify it. If they say to verify something, they're claiming that it's true, provided the textbook author didn't make a mistake. That's actually a solution, excuse me. This guy's actually a solution to this guy. But my equation doesn't look the same. Well, that's okay. At this point, you may need to do some algebra. You may need to do some back substitution to make this differential equation that you came up with look like the differential equation that they gave you. I've got an e to the t in this. I've got an x minus 1 squared in this. So let's go back to the beginning and look for a relation that we might be able to substitute to make this look like the expression that we want it to look like. So I'm staring at this, and then I go back up here. You see it? Remember when we exponentiated both sides and we got this relationship? If this implicit, or if this relation is satisfied, then this relation is satisfied. So that means that e to the t can be replaced by 2x minus 1, all divided by x minus 1. So I can replace that e to the t, again, by 2x minus 1 over x minus 1. This other x minus 1 squared, I'm just going to bring it down. I'm going to bring the dx dt down as well. And watch what happens. One of the x minus 1s will reduce. And if we distribute this negative through this set of parentheses, we get negative 2x plus 1, which is the same as 1 minus 2x times x minus 1. And it's the same thing. It's just written in a different order. We know multiplication is commutative, so we know that this is equivalent to the equation that they gave us. And we're good to go. If you're saying to yourself, what on earth did we just do? Let's recap. These are all equivalent. 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 This arrow, this like double, it looks like an equal sign with two little arrows at the end, but it just means that this equation is equivalent to this one, and this one's equivalent to this one. Or if you want, this implies this, and this implies this. It goes back and forth. Okay. So what did we do? We started with the relation that we were given, and we differentiated both sides with respect to the variable we thought of as the independent variable. And we chose t because of the form of the differential equation that we were given with. So we differentiate implicitly. And then our goal is to make, through differentiation, to make this expression right here look like this. If we can do that, and there's a function out there that satisfies this and this at the same time, then this is an implicit solution of the differential equation. And so we're just going to say that assuming that there actually exists a function that satisfies the relation as well as the differential equation, we have just verified that the natural log of 2x minus 1 over x minus 1 equals t is an implicit solution of the differential equation. Now, if you want an explicit solution, you could just do a whole bunch of algebra in order to get x by itself here. And then we could graph it, and we could see that there's a function that satisfies this equation that also satisfies this. Because this equation led to this, so we're good there. We would just need to find a function that satisfies this. And actually, that wouldn't be too difficult. To find an explicit solution, we would exponentiate like we did, and we would end up right here. And then you just solve this guy for x. It looks like a difficult thing to solve for x, but you'd actually solve this for x in the same way that you would solve this for x if you had this quotient equals 5. That e to the t, don't worry about it. It does not complicate the solution method at all. You would just multiply both sides by x minus 1 and get all the x's on one side and everything not involving x on the other. Factor out the x and then divide. So that's an exercise that you can do if you want to. Okay, so that is verifying an implicit solution. Now, most of the time in practice, if we solve a differential equation and we get a solution like this, and it's very difficult to solve for your dependent variable, we just call it an implicit solution and we're done. So you're going to see a lot of implicit solutions in this class, especially as we solve separable equations, which you'll see more of in the next video.